Hello folks, in this video tutorial I will be performing an explicit dynamics analysis in the 3D experience, which we know that buried in it is the ABAQUS program as the FEA solver. Now, I have done something similar to this in tutorial 6, except that here uh, we are assuming that this ball that is running into the flat plate is actually uh, uh, a pendulum. In other words, it's not coming in a straight direction, but it's swinging from some location and coming down. Now, uh, although it doesn't substantially change the problem from the one done in tutorial 6, but there are certain things that are worth looking at when it comes to modeling this problem. The other issue is that in this problem, I'm going to be modeling the sphere or the ball as a rigid set of shell elements. Okay, so but uh, but in order to actually make it rigid, define it as rigid, I need to mesh it with some elements, dummy elements, but the properties of uh, that sphere are not important because after all it's going to be rigid. However, I do have to put some dummy material on it. The plate is made out of aluminum, and the data is given on the next page. You'll see, and it's clamped at all edges. And after finishing this tutorial, in tutorial 8, I will be repeating the same problem, except that the sphere will not be meshed, will not be modeled as a rigid body. It's going to be modeled as an analytical surface, okay? But there are limitations with analytical surface. In other words, that surface must be either a surface of revolution or surface of extrusion. If not, then you have no choice but to model it exactly like when I'm doing it in the present tutorial. Keep in mind that although I'm using shell element to model this as rigid, but one can also use solid elements, okay? Because after all, it doesn't matter as long as it doesn't deform. All right, so here's the model in the 3D experience, except that this is for this line, this rope or cable or link is just for visual purposes. We don't actually model this thing, okay? Also, in the present problem, although I'm moving this thing for some angle, it could have been done by placing the sphere very close uh, to the plate, and then done the problem like that. Except that here it's easy; you get the illusion that it's coming from a distance and actually hitting the plate. And there is uh, the mesh of the plate and the shell mesh of the plate, and of course the dummy shell mesh of the sphere. This is taken from a following tutorial, which is done entirely in ABAQUS CAE. So there are some minor changes that I've made, but effectively, if you want to know what the counterparts of the thing in ABAQUS CAE are right here. Now, the whole purpose of the, these uh, uh, these these tutorials, at least in my YouTube channel, is show people who are either Abacus user or entirely new to the 3D experience how things are done here. This is why the examples that I pick in many cases are things that are done by other YouTubers using the Abacus CAE, and I replicate the steps. Okay, so the properties of aluminum are given here, the plate is given here, and the plasticity data is right there. Uh, and also I'm going to be using damage because we want to make sure that this thing actually destroys the plate, and we're going to use the shear failure damage model, and some values are given here which are just taken for illustration purposes, because to do damage problem you really have to know exactly what your material behavior is and things like that, and I'm just using the information from uh, uh, the, the, the the YouTube reference. Okay. Now the shell is going to be, or the sphere is going to be shell or mesh like this. Okay. Although this is irrelevant, these are irrelevant because after all, this is going to be rigid, and the information about the mass of this ball is not coming from the density of it. It's coming from I put a inertial mass at this reference point associated with the rigid body. Okay, so the 1.5 kilogram is the mass of this, but it's not coming from the density of it and the volume of it. Is assigned as a point inertia or mass inertia at this location. Okay. Also, the angular velocity of the sphere is a constant 75 radians per second. This is not the initial velocity; it's the constant velocity. So that means that even when it hits the plate, it keeps going. It doesn't slow down. It keeps going at that angular speed. Uh, in the YouTube reference that I gave you, the number of integration points was changed by from five default of 5 to 7, and the argument of the YouTuber is that it's for hourglass control. I left it the way it is, and but you please feel free to change it to 7. Let's see what the effect is. Now, here's what hopefully was going to come out of my channel, the total duration of this video. The total duration is 0.025 seconds, which means, yeah, it's right there, 25 milliseconds, okay? Yeah. Now, the plasticity data and the elasticity plasticity data, I've done it several times, so I'm not going to show you that, but I will show you the damage. The damage for the plate is you check damage, ductile metals, and one of the options that we have is damage, shear damage. That's what we're going to be doing. Now, notice that there are two uh, sheets here, and they're both there. That means that they're both activated. Okay. For the shear modulus, this is the data that I'm taking from the YouTube channel, and these have to be both checked. In other words, make sure that even if you're not putting numbers for this, at least you select it so that it is checked. I'll show you what the outcome is going to be if one of these, the second one basically is missing. You'll see that. But notice that when you select this, there's no data that I've inputted. This is the default values that were sitting there. Okay, I did not specify anything for this damage evolution parameter. Now, because we're doing this thing as a rigid body, an abstraction is going to be created. The point inertia is the reference point at the very top where I put my mass. That's your table looks like that. Uh, this mesh is for example, plate. This is for the sphere. These are the properties of the plate and the sphere, and these are the fact that the sphere is actually a rigid body. Okay. Now, in the channel the reference video that I showed you, at the time that this video was prepared by this fellow, uh, 6, 7 years ago, uh, uh, one could not do this thing through the interface in the ABAQUS CAE. They had to go to INP file and add stuff. Okay, but I didn't do that. We don't have that problem, and we just move on. And here's the restriction about the analytical rigid surface that I mentioned. So uh, this is why I'm doing this thing as a rigid body, and then come back in the next tutorial and do it as a analytical rigid surface. Okay, so let's go ahead to uh, the interface, 3D experience interface. I create an assembly, and immediately I'm going to save this thing. And then we're going to do the plate first. So right click, insert, 3D shape, 3D part. Okay. And I'm going to change the name of this thing to plate, October 15, plate, October 15, 2023. So this is the name of the instance, copy. Oh, that was the reference. This is the instance. This is for bookkeeping purposes, at least when I want to find things later on, I know where they are. All right, so let's go make it. Double click on 3D shape. That'll put us in either generative shape design or part design, wherever I was last. So on that vertical plane, I will sketch a square, which is 200 millimeter by 200 millimeter. Okay, let's give it dimension. And this is also 200. Exit. And since I want to mesh this thing with uh, shell elements, I have to put a surface through it, and surface has to be done in generative shape design. It cannot be doing part design. I am already there, so if I click on the surface, here is the fill, FIL, and this is already selected, so it puts a surface through it. Okay. Now let's go apply material properties. We can wait until the end and do that after I do my geometry, but I'll do it while up here. Tools, under material browser, I just go and add. The name of it, I'm going to be calling plate, October 15, 2023. Okay, and then we say okay. Now it's going to appear somewhere in the list. I select apply and then go back and apply to the part and put the here, right here, plate October 15. So I say apply. I don't need this thing anymore. Close it. So on the part and a check mark, and now I can go and input the values. Okay. So for structure, general option, density, this was 2770 kilogram per meter cube, which is properties of aluminum, typical aluminum. Now notice that here it says what is that, 2.77 into the minus 1 tons per millimeter cube. So basically I put it in terms of kilogram. Okay. And then you go to ABAQUS multiphysics, mechanical, elasticity, elastic, aluminum 70,000 MPa Young's modulus. That's too many. Okay, 70,000 MPa. Yep. Poisson ratio 0.34. Okay. And then we go to plasticity, metal plasticity, plastic, and I input the information from this graph. So 120 MPa, 0, that's a yield strength, and this is 240, and plastic strain of 0.3. Okay, takes care of this. Now we go to damage, ductile metals, and the different models. The one that we're using is shear damage. Check that. And the number is 0.3 and 0. This is what I'm putting in, 0.3 and 0. And notice that the second one should also be checked. So this is okay, but make sure that this damage evolution is also activated, but you don't have to put any numbers here. I will come back and get rid of this and show you what the effect is going to be. So that's fine. This is all done. Let's do a quick save here. And now we're going to insert the pendulum. So we go all the way to the top, right click, insert, I'll call it the sphere. Uh, insert 3D part. Okay, let's rename this thing. Right click, properties, sphere, October 15, 2023. So this is the reference name. Right click, copy, and so that was the reference name. Put it as that was the instance name. I put it as a reference name also. But these are habits that I have from CATIA, the CATIA program. Okay. Now let's go make it. Double click. And what I'm going to do is first I'm going to create a point up there. at the location that I want. So under wireframe, create a point 500 millimeters above the Z direction. That's going to be my reference point later on. So right there, see that? And then I'm going to draw on this vertical plane a line going like that. I'm going to later on make it coincident with that point, no problem. Do that. So this point, control that point, either zero dimension between them, or my preferred way of doing it is through this constraint box, say coincident. Okay. All right. Now let's put some length on this. This is 500 millimeters. So this is 500 millimeters. Yep. And this angle, the angle from here to there, the angle from here to there is 45 degrees. Okay, I think that's very good. And then we exit. All right. Now I want to make a sphere right there. So the question, how do I do that? Sphere is a surface. You go on the surface. You go under this basic operations, extrude, etc., revolve, and there's a sphere. You click on the sphere. It says, where is the center? The center is this location. What is the radius? 37.5. Okay. And default axis, that's fine. So we say okay. Oh, these angles, if you look at it carefully, you see that it's not the full sphere right now. You can see that. So to make it a full sphere, you have to change this angle to minus 90, and this goes from 0 to 360, and that'll give me the full sphere right there. Okay, let's apply our material to it. So tools, create a material. We'll call it sphere, October 15, 2023. It's going to be somewhere in my list right there. Apply, get rid of this, apply it to that part, and we plug in our dummy values because, as I said, this information is not going to be used for calculating mass and things like that. The mass is going to be put as a point mass later on. So structural density, I'll put properties of steel there. As I said, totally irrelevant. 7850, how about that? Something like that. Okay, and for Young's modulus, I mean, you can put anything you want here, but I'll use properties of steel. 200,000 zeros, MPa, Poisson ratio 0.3. Yeah, these are standard properties from steel. No plasticity, no damage, etc. So we're going to say okay. Quick save. All right. Now we're going to do the meshing. So the easiest way of doing this thing, you do it at the assembly level all the way to the top. Make sure you go all the way to the top. Make sure you're not in these things where you create your mesh. I want to create at the assembly level and go to structural model creation. That's where the meshing is done. Like you can see the icon. Looks like there's some mesh on this piece. Yep. MTFEM model because we're going to be creating it manually ourselves. Okay, good. It says there's two parts here. Which one of these do you want to participate in your model? Well, I want both of them to participate. Right there, both of them. And we say okay. All right. Now, Why don't we mesh the plate first? So let's go to mesh, uh, quad mesh, surface quad mesh over here, and the type. I think in the video I'm suggesting 6 millimeter, although these are not very sensitive at this point. 6 millimeter mesh it. You can see that right there. Say okay. Why don't we apply properties to this? So we go to the properties, shell property, and we can do it either by plate or by element. That's entirely up to us how we want to do that. Let me do it by element. So these element thickness of that plate is 2 millimeters, right? 2 millimeter, 200 by 200 by 2. Okay, and that's pretty much it. Here's the property for that. Oh, you know what? Let me go back here. Let me show you what happened. Double click on this. It says I don't know material. And the reason it doesn't know the material is that because I selected surface quad mesh, but that material was put on the surface. Okay, so let me make my job easier. Let me clear this, remove this. But for that, I select the part. Now, when I select the part, it knows what the material is. Otherwise, I had to go and use the magnifying glass and find this material and apply it to my elements. No problem. Okay, good. Let's go and do the mesh for this piece. Okay, so let's go ahead to the mesh again, and we do once again a surface quad mesh on this. I think in the slide I'm saying 8 millimeters. Doesn't matter. Oops, not 88. Mesh right there. You say okay. We're going to apply the properties. So property, uh, shell section. Once again, I select this so that the material is picked. Otherwise, I have to go and select the material from this magnifying glass. And the thickness is totally, these are totally irrelevant, but the thickness, I think I put down 5. Now remember, the thickness, and the density, these things will affect the mass, but not if you're declaring it as rigid in a minute. Okay, if it's rigid, then it doesn't matter, and we actually apply the information at this reference point. Okay, so let's go ahead and do that. Under abstraction, there is this icon here, abstraction. Under the abstraction tab, there is this icon that says rigid body. There's also analytical rigid surface, which we're going to do in the next tutorial. Rigid body. You click on it, and you select this entire thing. The whole thing is going to be picked, one sphere. And the reference point, see that? There is a reference point. It's specified. So I'm going to select that point 1. That point 1. Uh, let me do this thing point 1, although I'm pretty sure there's no issue with the vertex, but I'm gonna remove this and make it point 1. Now, why that point 1 is over here? I'm 99.9% positive that vertex would have worked, but there we are. Okay, point 1. Okay, and now we apply point inertia to that reference point, which is point 1 right there. Uh, the unit here is tons, so I'm going to put 1.5 kilogram. It's going to convert it to tons, but of course it's going to round it off because there's 3 digits that are used. It says 0.2 tons, 0.002 tons. Okay, you can say, oh no, not tons, kilogram. Okay, and it's going to convert it to 0.002 tons. This is actually 1.5 because there are only 3 digits displayed here. I can change that, but anyway, this is 0.25 kilogram, 1.5 kilogram. Now these things are irrelevant. Okay, however, the user the YouTube user has specified these things, but uh, let me also use the value, but those are irrelevant. As a matter of fact, let us, yeah, okay, so 0.77. These are the mass moment of inertias, but this guy is not uh, needing those. You're not needing the spinning motion. So, but anyway, let's do it. Okay, good. Here's the icon for the mass up there. All right, so this is it. Save everything. We have done all the meshing stuff like that. Okay, so now we're going to go to our FEA solver. But remember, you can go there, structural scenario creation, but this doesn't have explicit dynamics in it. I have to go to mechanical scenario creation. That does have the explicit dynamics, so I go there. And I want a structural. I want the model that I created. Let's give it a minute. Okay, incidentally, before we do the rest of the problem, I want to point out, expand this tree here and show you what these things are. These are exactly what you saw in the slide. Okay? All right, good. Let me uncheck that. Okay. So now we're going to go on the procedures, uh, explicit dynamics right there. See that? Explicit dynamics and total duration of 0.025 second. Everything else default. Good. No, now I have both green check marks. Okay, so let's go and apply our boundary conditions. The boundary conditions, these four edges are clamped, and I start picking these. It won't pick it. The reason is that that sketch that I drew in order to put this thing on it is showing. Okay, so let me do the following. Okay, so I have to take these four edges. Okay, so what I have done, if you're having issues selecting these four edges, the easiest way is to go there to your model, plate model, and make sure you hide the sketch from here. If you display it, notice that I cannot pick these edges. Okay, I can pick the whole fill, but not the edges. So I'm going to hide the sketch from here, and now I can select the four edges. 1, 2, 3, and 4. Okay, that takes care of this. And I want to take that point 1 and prevent it from moving except for rotation about the y-axis in this case. So we go to again, we are in boundary condition, but use the fixed boundary condition, fixed displacement. So you select that point 1 from the tree. If I do it from here, I may have a problem. Pick up the vertex. Again, the easiest way is to go to a part here instead of fooling around with the visibility manager. Here's the point 1. I took it from the tree. Does not translate. Does not rotate about x and z, but it rotates about y because the pendulum has to shrink. Okay, that takes care of our stuff here. So let me do a quick save. And now I will go and apply my my velocities. So uh, here is on the boundary condition. This is applied translation velocity. No, I want rotation. Applied rotational velocity right there. You click on it. Once again, select that reference point 1, but it's about the direction y, and the value of it is 750. I changed that from the other video, so reference video on YouTube. So right now 775. Okay, it's going in the right direction also. So we say okay, and oh yeah, now the contact. So you go to interaction, define the contact coefficient on the friction, specify friction, 0.3 that was given on the slide. Okay, and then we do a general contact. So make sure the appropriate contact model is selected, friction value selected. Contact property 1, that's the one that I just created. You say okay. So it's going to be, everything is going to be done automatically. Let's do a quick save, and we are about ready to start the running. It's always a good idea to go and check the model and scenario check. I don't see any problem there. Then do a simulation check. If anything obvious missing, it may be able to tell us. Oh, you know what? I forgot to change my element type to reduce integration. So I'm going to stop this. I'm going to say cancel that. Let's go back to our element type. So we go to structural case, element type, double click. I'm going to change this to reduce integration. Okay. All right. And now we're going to do, I'm not going to do the model check, but we'll do the simulation check. Hopefully I didn't forget anything else. Notice that in this video, I prepared the mesh at the assembly level. I could have done it at the part level and asked the software to include those. And I will do a video segment on the, 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 the issue of the assembly of meshes or mesh of an assembly. So basically, I did mesh of an assembly, but we could have done it as assembly of meshes. There will be a separate video for that. So close that. Not in this playlist though. And now we're going to run it because it didn't give me any warning, any errors. Now we're running it, okay? And it's going to be very fast, I promise. It hasn't started running yet. Okay, now, from now, when I say okay, it'll start running. And we can monitor the progress. As ABAQUS users know, there's a button there called monitor, which shows you the progress of this, but here it's not called monitor, it's under iterations. Okay, that's the wall clock, wall time. Yep, probably take about 50 seconds. This is true seconds, not CPU seconds. Yeah, 59, 64%. Yeah, less than that actually. We're almost there. Okay, took roughly 20, 25 seconds. Okay, so let me close this. So here's the situation. There's the ball. I can't see it because this is rigid surface. We're going to fool around with this thing so that we can see it better. Now, initial condition, then the ball is moving. You can see that the ball is moving. It hits the plate, incurs damage. You can see that, and goes. Now, one of the reasons that this may look a little bit different from that is that here, I think when I made this run, I made it to 5 millimeter thickness, but today in this video, I made it 2 millimeter thickness. Now, a couple of things. First of all, you can do an animation. Okay, we can slow it down. Let me exit that. Okay, now what I want to do is go back. Remember, oh yeah, before I do this, double click on this. In this tool, in this dialog box, if you go to this options, sorry, not options, this rendering, say show me the elements too, show me the mesh. This was just the outline. If you say show me the mesh, apply, you can see it better. Okay, so for example, you can see that what happens. Okay, now the other thing is that let's go to our analysis. Let's go to our analysis. Analysis meaning that uh, where I specified the material, actually, that's what I mean. So we go here to our material, see where we can find it. A plate, was plate, yeah, plate. Here's material, there, double click on it. There's material for plate, double click. I will go and remove that damage evolution. That's gone. So this is still there, but this one is gone. There's no white paper here, white sheet here. And I'm referring to this issue. Okay, I removed it and I say okay. And now go and run it. Let's go to our scenario. Oh, here it is, physics simulation. And now we're going to go and run it. Let's go to scenario. I'm not going to bother doing these two. I'll just literally go run it. Okay, hopefully nothing is a problem. Let's see what happens. I won't run it until the very end, but I will stop it and look at the results. When you stop it and look at the results, obviously you didn't finish the run. ABAQUS users call this thing, you have to do a restart, but I'm not interested in it. I just want to see what is the effect on removing that damage evolution parameter. Okay? As I said, we're not going to run it until the very end. After a while, I'm going to stop this and then try to look at the results. Still let it go, because notice that it'll take the time for the pendulum to swing and reach the plate, and then it's going to hit it. So when it hits it, we can look at the plot and some kind of a bump, in the curve. So, but let's just wait. Right now, it's 54% completed, right? When it reaches 60, 65, 65, probably I'll stop it. Yep. Okay. So I'm going to stop. Maybe 70. Okay. I'm going to stop this. This tells me that, hey, if you stop that, you can't see the whole thing. Say, fine, because it didn't complete it. I'm going to close this. Okay, I'm going to close this. Go to the results. Fine, it says that use interrupt. You see this? It just does not do what we expect. Remove those elements. Okay. So the reason, well, at least in this case, if I don't activate this, it won't show me the damage. It won't. And to do these damage problems, you really need to know about damage mechanics. Okay, so that is not the focus of these tutorials. The ball is still here, by the way. Inside, right there. Okay, that's pretty much it. Good luck. So the next video, video 8, is going to be exactly the same thing, except that I will use analytical rigid surface for the ball. Good luck.